to this course on computational thermodynamics and kinetics of materials. Today we will see some of the essential concepts for overall transformation kinetics. These are going to be the contents. Diffusional transformations and interfacial phenomena. We will explore this. First we will see diffusional transformations mechanism, which is nucleation and growth, and diffusion is part of these things, but this is not only diffusion. Okay, and bulk Gibbs energy change is the Gibbs energy change that we have been considering till now as the driving factor for diffusion. That aspect will be there, and on top of that there will be barriers for this nucleation and growth, which are called interfacial energy and strain energy aspects, and then how nucleation rate depends on all this. Now we are talking about rate, and kinetics will come into picture here, and then growth rate and phenomena such as impingement, which also must be considered. Then how diffusion occurs through defects, essentially the fast diffusion paths, and how all these things are put into overall transformation kinetics and studied. Okay. So let's take this case of product phase forming inside the parent phase through diffusional transformation. What we know about this is there will be a Gibbs energy change for the product to form, that delta G parent and product in their bulk form. It's called as Gibbs energy change bulk, delta G bulk. In fact, we have not used this word bulk till now. It essentially means that atoms are in stable position. You see the potential energy curve that we have seen at the very beginning about internal energy when we studied. This potential energy curve is telling you that what should be the lattice parameter or the equilibrium distance between the atoms, right? So that tells you the potential energy in the internal energy part, and the internal energy is part of enthalpy and it is part of Gibbs energy. Therefore, what we are talking about bulk Gibbs energy is considering the fact that all atoms are nicely bonded in their equilibrium positions. Okay, what about the atoms which are not in equilibrium positions? So they are going to have different Gibbs energies. That is basically the interfacial phenomena that we are going to deal with. So consider this kind of a phase, parent phase. Inside that there is a product phase forming. Okay, you can imagine this as a grain, and inside that some other product grain is forming. Okay, and there will be an interface like that, right? This red color thing is an interface between parent and product. Basically meaning the surface of the product phase, which will not have atoms arranged in proper manner, and exactly at that location even parent phase will not have the right neighbors to bond. Therefore, the atoms that are there in the interface are not going to be having the minimum Gibbs energy. That is, they will not be in their stable position. Okay, let us focus on this particular part here. If I expand that, this is how we will be seeing the interface. You can see this is the product phase, the atoms in the product phase, and these are the parent atoms here. Okay, what you see here as the red line is the interface, and you can see that the atoms which are white atoms here do not have white atoms to bond across this. Okay, and these hollow atoms of the parent, they also do not have the right parent atom here to bond. So therefore, these guys here, these atoms, do not have right atoms to bond. Therefore, they will be slightly in a higher Gibbs energy state, not in their most stable form. That is point number one. So this product formation requires an interface. Interface atoms have no proper neighbors. Therefore, they possess higher Gibbs energy, and that is called as interfacial energy. If they are in the surface rather than the interface between two phases, we call it surface energy. Okay, so this is interfacial energy here. It is a barrier for the transformation, isn't it? Because if atoms have to come into this configuration where they do not have proper neighbors to bond, it means we have to create atoms with a higher Gibbs energy. If at all a transformation has to happen, product has to form, at least a layer of atoms should be generated which have higher Gibbs energy, not the Gibbs energy of the product. Okay, and then there are strain aspects. See, if you see here, the atoms here, these two atoms are at their stable position with certain distance, but but as we go near the interface, the atoms are getting stretched because they have to, if at all they have to maintain this coherency, we call this coherency, the right bonding you can see. It need not have right bonding like this, but if at all they happen to have bonding with the atoms on the other side like this, then we call this coherency. And if this coherency has to be maintained, then the atoms are to be stretched like this. So this stretching causes strains, right? Meaning the atoms are not in their most stable form again. So the atoms, the few layers near the interface are not having their most stable interatomic distance. Therefore, they are at a higher energy. So this energy is not called as interfacial energy. This is called as strain energy. Okay. So there are strains near this interface, and atomic bonds are stretched because of that. And the atoms which are experiencing this stretching, they possess higher energy, and we call it strain energy. Okay. It is another barrier for the transformation. So both these things, the interfacial energy and the strain energy, are barriers for transformation. If one of the phases, let's say the parent or the product, happens to be liquid, then the strains can be accommodated easily. Atoms can move and the strains can be accommodated. If a liquid is involved in the transformation, the strain energy aspect will not be there. But in the solid-solid transformation, it will be there. Okay. So let us take this solidification and understand this interfacial energy a little more. Okay. Let's say this is liquid, and inside that there is a solid forming, and the mechanism of transformation is nucleation and growth. Okay. In solidification. Nucleation means this: a nuclei is a stable cluster of atoms in product phase crystal structure and composition. Okay. So there is a product forming, the crystal structure and composition of the product phase is achieved here, and it's a stable cluster of atoms, we say, because there are possibly few hundreds of atoms coming together. Okay. So if the reason why we say stable is, if at all it is smaller than a critical size, it will dissolve into the liquid again. Actually like this, if you see these grey atoms are the liquid atoms, and this is a cluster with the product crystal structure and composition, but the atoms that are white are the product phase atoms, and these red atoms are also product phase atoms, but they are at the interface. Okay, so they represent this red line. Of course, this is a very small nuclei that I am putting here for understanding sake. Few hundreds of atoms like this can come together to form nuclei, and you can see this cluster, this nuclei is smaller compared to this. Which one will be stable? Okay, there will be a cluster of a critical size. If product atoms come together, if the atoms come together in the product shape to a critical size, only then they will be stable. You will understand this why. Because this surface energy is like this. This interfacial energy is drawn like this. It's a positive value. Okay. So this is a surface Gibbs energy. Okay. I am putting it in this Gibbs energy versus radius of particle graph. This radius of cluster is here. If the radius is very small, let's say here, it will have this much interfacial energy. Okay, it's a positive value. And if you see this curve here, this is the bulk Gibbs energy change, that is delta G bulk, meaning if grey atoms become white atom, how much will be their Gibbs energy change. Okay, that is what bulk Gibbs energy change means. So if bulk Gibbs energy change is negative value all along, there is a competition between this interfacial energy and bulk Gibbs energy change. You can see that. And for a smaller nucleus, for smaller clusters, you will see that interfacial energy, the positive value is dominant over this negative value. Therefore, if we do the summation of both and plot them, it will be like this graph. Okay, this is the delta GR, Gibbs energy change of nucleation, meaning the summation of interfacial energy and bulk Gibbs energy. Okay, so that is this graph. So this graph is going up, actually it is not going down. The fact that it is going up tells you that for all these sizes of nuclei, the clusters forming, they will have a positive Gibbs energy change. This delta GR keeps going up, reaches a maximum and then starts decreasing, meaning beyond a particular size of this cluster, you will see that the Gibbs energy is dominated by the bulk Gibbs energy change. The Gibbs energy change of nucleation is dominated by bulk Gibbs energy change. That's the reason why it is overcoming the interfacial energy aspects and making the entire delta GR negative. So, but from this point onwards, keeps decreasing. Although delta G is positive here and maximum, from that point onwards, it keeps decreasing. It means that if at all a cluster of this size comes, let's say the product atoms form in this particular size or any size beyond that, the addition of any atom to that to increase its radius is going to decrease the energy. You see, the radius is increasing and energy is decreasing. But the cluster should come to this size spontaneously, only then it can start becoming bigger and bigger, only then it can start growing. Okay, so this sized nuclei is called critical nuclei, and addition of one atom to that, let's say an atom, the gray atom jumping to that, that is nucleation. Okay, a critical nuclei becoming a stable nuclei, that will happen after this radius. So this is the radius of critical nuclei. Okay, so this particular graph, which is so elegantly explaining the competition between interfacial energy and bulk Gibbs energy, tells you that you need to have a cluster coming up with a certain size, only then it can be stable nuclei. A stable nuclei will grow. Okay, in that way, this interfacial energy, you can understand, this is a barrier to nucleation. We were till now, when we considered thermodynamics, we have been thinking only about this bulk Gibbs energy change. If a product phase has a lower Gibbs energy than the parent, the product will form. This is how we have been discussing all along. Now we are bringing in aspects such as interfacial energy, which are part of this transformation, but they are positive energy changes. They are not negative energy changes. So therefore, that positive energy change should be supplied by the negative energy change that is happening, meaning the driving force should be sufficient enough to balance the effect of interfacial energy. Since this interfacial energy is a barrier, there are different kinds of ways in which the system tries to minimize that, or tries to find a path where not much of a barrier is there for a product phase to form. Okay, that's where different types of nucleations come. Okay, two types of nucleation are there. Homogeneous nucleation is where uniform nucleation rate is seen everywhere, meaning look at this nuclei here. If such nuclei form everywhere at uniform rate, any volume of material you take, number of nuclei there are same. Okay, the nucleation rate is uniform there. Whereas this one here, this is forming near this boundary. Okay, this boundary is a heterogeneous nucleating site. Okay, why? Because it is giving this kind of a interfacial energy, a low interfacial energy. The reason why this is not red but yellow is because there is a lower interfacial energy at these boundaries, because it's a solid-solid interface, not solid-liquid interface, and these two solids have such matching that the interfacial energy is lower there. So therefore, rather than forming a nuclei like this with so much of interfacial energy, which is a barrier, this kind of nuclei formation can minimize that. Therefore, there is a preference for nuclei to form in these sites, and let's say the walls of the container where the liquid is kept. If it is a solid-solid nucleation, the grain boundaries become nucleating sites. Okay, so they are called as heterogeneous nucleating sites. Definitely, the probability of finding nuclei is more at the heterogeneous nucleating sites. So that is heterogeneous nucleation. Okay, so the nucleation rate is going to depend on definitely this interfacial energy and this bulk Gibbs energy change. This bulk Gibbs energy change will be more if we go to lower and lower undercooling. In terms of solidification, if we see, it is function of undercooling. What is this undercooling? If you imagine this curve, Gibbs energy versus temperature, we know when melting happens, when solidification happens. So FCC, let's say this is some material where FCC is the solid state. At high temperatures it is liquid beyond melting point. So if we bring the liquid below this temperature, we are going to make the FCC stable, the solid stable. If we bring liquid directly to this temperature here, we will see the difference between liquid's Gibbs energy and solid's Gibbs energy is this much. That is the delta G bulk, isn't it? Then instead of this temperature, if we directly bring liquid to this temperature, okay, then we will see liquid to become solid, there is a very high driving force, delta G bulk is really high. So this is undercooling. From the melting point, how much below we are coming, what is the temperature to which we are bringing, the difference between the temperature, this melting point and this temperature is the undercooling. Okay, so this undercooling, if it is more, we see that delta G bulk is becoming more. Therefore, this delta G bulk is a function of undercooling, delta T. So therefore, the higher the undercooling, the more the delta G bulk. Is that all? Interfacial energy and bulk Gibbs energy depending on the undercooling, are these two things the only thing that control the nucleation rate? Actually no, there is this other aspect of diffusion, because if liquid atom has to join the solid, it has to jump, the jump frequency is important here. Therefore, this diffusion aspect also is important. It is an important aspect that affects the nucleation rate. So when we talk about nucleation rate, since we are dealing with kinetics, we have to talk about nucleation rate. It depends on the surface energy, the interfacial energy, and the delta G bulk, the driving force, and this D, which is diffusivity across this interface. So all these things matter when we talk about solidification kind of transformation. If we go to solid-solid transformations instead of solidification, we will see one more aspect coming, that is nucleation rate is going to depend not only on gamma, delta G and D, it is also going to depend on epsilon, which is the strain energy part. Okay. So you remember this. So if at all solid nuclei forms with the parent, if it has this kind of coherency, then it has to experience this strain energy as well. Okay, that is an extra energy that is also going to decide the nucleation rate. If it is high, then there is a higher barrier for nucleation, right? So if once nuclei forms, it has to grow. So in growth also, all these aspects are going to play a role. Interfacial energy, if the interface has to grow, interfacial energy matters. Then if it is a solid-solid transformation, strain energy also will be there along with the interface. So that is also going to matter. Delta G of course is the driving force. If it is more, growth rate will be higher. Then obviously the one which we have been seeing till now, any growth depends on diffusivity. That is also important. So all these aspects are important in deciding nucleation and growth. So are we done? Are these the things which are going to affect the nucleation and growth? There are more aspects, phenomena such as impingement. It intervenes the growth. What is this impingement? It is this physical space, diffusion and thermal fields. Diffusion field and thermal fields overlap and the growth accordingly changes. What are we talking about? You bring this nucleus, let's say a couple of nucleus like this, and I am putting some more area like this in a light grey shade. You can imagine that area to be where the diffusion field is. For example, where near the interface, if you remember, there will be more diffusion activity because the equilibrium partitioning happens there. So the product phase and parent phase will follow the composition shown by the tiling. And then the bulk of the parent phase can still have the overall composition, but near the interface where most of the diffusion activities happen. And if you remember in the all diffusion simulations, we have been focusing more points of calculation near the interface. It is for that reason. So we call that region diffusion field. So if the diffusion fields are like this, here and here they are not overlapping, but as the growth achieves near completion, you can see that these fields overlap and the atoms here must be distributed among both the fields. So that is where the regular growth that we will be predicting may not work. We have to consider this other aspect of fields overlapping and impingement happening and all. So this is difficult to simulate. So if we are simulating, let's say, or we are trying to understand one full transformation, we should not be focusing only on diffusivity and how it affects the entire transformation. We need to know the interfacial phenomena, the strain energy, the interfacial energy. All these things are important, and towards the end of transformation, things like impingement also matter. Okay, even the physical space is now overlapping between the two grains. So they have to stop considering the fact that there is the other grain coming near that. So apart from all these, some more aspects of diffusion itself, we have been dealing with diffusion as if diffusion has only one diffusivity value for an element in an environment, but it need not be. The environment that we are talking about need not be a perfect lattice. If the lattice has defects, then diffusion through their defects will be different. So in that way, all these crystal defects, vacancy, dislocation, grain boundary surface, we have to consider all of them. Especially this lattice diffusion is what we have been talking about, that atom jumps from its original location to the next location and forms bond again. So this particular thing is lattice diffusion. When we talk about dislocation pipe, it is the core of dislocation. Dislocation, if you have already come across, you may know this is basically a line defect, a line of atoms which do not have proper neighbors to bond. Therefore, they are at an excited energy level. and the area below the dislocation line is called as dislocation pipe, and diffusion through that pipe is easier. And diffusion through grain boundary is easier. This is a two-dimensional defect. Surface is also a two-dimensional defect, and diffusion through that will be even easier. Okay, so defects are faster diffusivity paths. Why? Because the atoms are less orderly arranged, therefore they have high energy, high Gibbs energy, and it is easy to break bonds and make bonds through such areas which are basically excited and ready to change. And this is the hierarchy. Lattice diffusion, compared to that, dislocation pipe diffusion is faster, grain boundary diffusion is faster than that, surface diffusion is faster than that. Okay, all these things that we have seen are beyond bulk thermodynamics and kinetics. You could have sensed it by now. In phase transformations, an interface occurs between parent and product, and nucleation and growth occur and depend on gamma, epsilon, delta G bulk and diffusivity. Okay, interfacial energy, strain energy, driving force and diffusivity. Okay, diffusion is faster through defects such as surface, grain boundary, dislocation pipe. Okay, other phenomena such as impingement matter towards the end of transformations. All these aspects are studied under overall transformation kinetics. So compared to what we have been doing till now, where one interface moves, the interface motion is not a problem at all. Therefore, the diffusion is the only thing that controls an interface movement. Now, after this class, you can sense that the interface need not be moving at infinite speed every time. If the interface has so much of problems, then interface growth itself can control the process. Diffusion is definitely a problem. Diffusion should happen for the transformation to complete. On top of that, this interfacial phenomena can also play a role. If it plays a dominant role than the diffusion, then we call the entire process as interface controlled one, not the diffusion controlled one. Okay. So these aspects are important when we are talking about overall transformation kinetics. Okay, how to understand overall kinetics of transformation? There are different ways. We will see few of them in the next class. We will also do hands-on sessions on this. Fraction of product versus time plots. This is one way to figure out overall transformation kinetics. And there are time, temperature transformation diagrams and continuous cooling transformation diagrams. So we'll see both of them in the next class. Thank you. I hope the lecture is useful. See you in the next class.